have an assignment for last night. If you had questions over any of the previous, we'll still go over those even though we didn't immediately cover that.
May I have your attention? May I have your attention, please? It's now time to dismiss the softball girls. It is now time to dismiss the softball girls.
Since you do have that out here. Okay, good. So, all right, guys. Where we stopped yesterday was horizontal stretch and shrink and vertical stretch and shrink. Vertical stretch and shrink. We'll look at it first. Vertical stretch or shrinks, general form is A times f of x, where A is the amount that we're stretching or shrinking the function by. So if it says it's a vertical stretch of 3, the value of A is 3. If it's a vertical shrink of 1/3, A is 1/3. So the amount that we're stretching or shrinking it by is going to be this A value. Doesn't matter if it's a stretch, doesn't matter if it's shrink, we plug that amount in for A. And do essentially what we've been doing with like reflection across the x-axis, we then apply it through. Good with vertical stretch so far. I think it'll make a little more sense, especially when we start actually applying a vertical stretch to it. One more. Right there. Now, I don't really like the wording for horizontal stretch and shrink. I will explain why here in a second. But if we look at horizontal stretch and shrink, it says the graph of y equals f of ax, a times x, is a horizontal stretch or shrink by a factor of 1 over a. Of the graph of y equals f of x, where a is greater than 0 and a is different than 1. I don't like the fact they use a in 2 different places. And it's showing 2 different things. Do y'all see that? I wanted one of those at least to be a different letter, some way to specify. Now what they're saying is that before a, so multiplying the inputs by a before evaluating the function stretches the graph horizontally, where 0 is less than a is less than 1, and shrinks the graph horizontally towards the y-axis when a is greater than 1. So when they give us the amount, they say that it's going to be here a horizontal shrink of 1/3. So they're saying that we're shrinking the graph horizontally by 1/3. A that we plug in to the graph into the function is not 1/3. The value that we're plugging in for this A is going to be 1 over 1/3. That's our 1 over A. That's why I don't like the fact that it says f of a times x is 1 over a. I wanted one of those at least to be something different. Horizontal, we have to flip it. So the value we plug in for this horizontal shrink of 1/3 is not 1/3, but it's flip, which is 3. If I can grab a calculator, I can say 1 over 1/3, which is 3. If it says it's a horizontal stretch of 5/3, we would say 1 over 5/3 or 3/5. We just flip it. That is the big thing with horizontal stretch or shrink. Whatever value they give us, we have to flip it before we plug it in. And out of all the transformations we've done today, that we'll do today and that we did yesterday, this is the only one we're actually having to do something to the value. Now the question is, what about left, right? Well, left, right, we just looked. What did it tell us? It was moving left 3. So h's value that we plug in for h is -3. right 2. H's value is positive 2. We didn't change it. We didn't mess with it. This is the value. We plug it in for H. We plug it in for K. We plug it in for A. We plug it in. This is the only one where they tell us, oh, it's a horizontal shrink of 1/3. Okay, I take the 1/3, flip it to become 3. Now I can actually plug it in. We kind of see that? Only one we do this with is horizontal stretch and shrink. Once we remember that, it doesn't work. It works essentially the same thing as the rest. We just have to remember with horizontal stretch and shrink, specifically and only horizontal stretch and shrink, we flip that amount they tell us. Vertical, we'll do vertical first. It's a little bit nicer. I want to vertical stretch and shrink. So let f of x equal the absolute value of x minus 3 minus 5, whose function h, so we want a function h of x, whose graph is a vertical stretch, general form a times f of x, vertical stretch of the graph of f by a factor of 2. Vertical stretch, the standard form of it is a times f of x. What is the value of a? How much are we stretching it by? A factor of what? 2, yes? So the value of a is what? Okay, let's replace it. We know a is 2 for this here. So we're saying 2 times f of x. Questions on how we got 2 times f of x? All right, we still have f of x, yes, for finding this function. So I'm going to replace f of x with its function. Absolute value of x minus 3 minus 5. Questions on how we got to this point? Now we just need to simplify. We got to multiply through, yes? So that 2 is going to multiply with the absolute values. And just like with the negative yesterday, when we multiplied through with that negative for our reflection across the x-axis, that 2 is just going to hang out in front. Multiply with whatever sign or number is in front of the absolute values. Then we're also going to have to multiply that 2 with the negative 5, which is going to make it negative 10. Questions on this here? That's it. So with most all this here, again, we're just sticking to these general forms, plugging in the numbers, plugging in what we know, simplifying it. Questions on this here? Now the next one we look at here still have the same function for f of x, but we want to write a function g of x, whose graph is a horizontal shrink of the graph of f by a factor of 1/3. General form for horizontal shrink is f of a times x. Bless you. Now they gave us 1/3. Is the value of a going to be 1/3? No, we've got to what? Flip it, because we're talking horizontal shrink. So when we flip it, a is 1/3. Because if it's helpful to write out the fact that it's 1 over 1/3, which gets us to our 3, do that. But again, we're flipping that 1/3. We've got to flip it to find out the correct value we're plugging in for a. So when we look at this here, it's going to be f of 3x. As we flip that value of a to find, we flip this, what we're shrinking it by, to find out the correct value we're plugging in. Questions on what we've done so far? We flipped the value they gave us and plugged it in. Do we have f of x anymore? No, we have f of 3x. We replace the x with 3x. So in every place in the function, we have to replace the x with 3x. So we'll have the absolute value of 3x minus 3 minus 5. There's no number in front of that parentheses around the 3x. There's nothing attached to it, so we can just drop the parentheses, giving us the absolute value of 3x minus 3 minus 5. That's it. X minus 3. That's our absolute value function. So that's the graph. So we're saying that we're shrinking it horizontally. So horizontally, left and right, what we're saying is that it's going to increase slower. Now, one of the interesting things or the weird things with horizontal, it is going to make it increase slower. So the sides of the absolute value are going to be closer together because we're shrinking it horizontally. It's also going to move the vertex, that smallest point, a little bit too. It's going to mess with a few things. Because if we look at this here, math, absolute value. Because, and I'll show you this here, I'm going to plug both of them in. X minus 3 minus 5. We'll turn this one off. Math, absolute value 3x minus 3 minus 5. Because this is the equation we got, yes? So it moved the vertex, that smallest point, over a little bit, but the sides of this absolute value are indeed closer together. It did shrink it horizontally. There is a horizontal shrink, yes? And we can see that because knowing it and seeing the graph of it, okay, this makes sense, yes? Now, instinctually, it feels like we should just be able to leave it as 1/3. Let's see what happens if we had left it as 1/3 and done the same thing. No, it definitely got wider. This is why we're having to flip it, because that amount, when that number's put in, is acting differently than what we would expect. The opposite of what we expect. So especially if we're looking at the graph, that value of A, that horizontal stretch and shrink, that number is going to be in front of X, inside the parentheses, inside the absolute values. And just like left or right, it's the opposite of what we think. Okay? Does that make sense? Yes? Okay. Might just be me. But again, horizontal stretch and shrink, especially if we're looking at the graph, it's the opposite of what we think. Now, there is other things that go along with it. I won't have you look specifically at this and say, what is the horizontal? What is the transformation from the parent function for this here? Because there is some small quirks to it on how we would have set it. We're not going to worry about it. We're just going to apply it. Okay? Let's look at another one of these horizontal. Write a function g whose graph is a horizontal stretch of the graph of f by a factor of 5. Horizontal, f of a times x, f of ax. Our value of a would not be 5, it's going to be what? 1 over 5, 1 over that amount. Now that works out nicely for us here because, well, 1 over that amount, 1 over 5 is 1/5. We flipped it. We don't have to simplify, we don't have a fraction and a fraction, so we're good. So that means the number we're plugging in for A is 1/5. X minus 1. Since we have f of 1/5 x, we can replace every x in the function with 1/5 x. Question how we got to this point here. Do we need those parentheses? No. And yeah, that's a fine way to do it. We can just erase them. Because we can rewrite it. There's nothing wrong with rewriting it without the parentheses, or we can just erase them. That's it. How do we feel about horizontal stretch and shrink? Feels like there should be a lot to it, especially as much as I talked that up, but once we see the flip, we're good to go. We'll do one more vertical, just so we see one more vertical. There's this one. I think there's one more after it. Which vertical do y'all want to do? This one or, I can't remember if the next one's vertical too. Yeah, this one or the next one. Yeah, we'll do this one, 0.25. So this is a vertical shrink of the graph of f by 0.25. So write a function h of x whose graph is a vertical shrink of the graph of f by 0.25. So what's the value of a? 0.25. So I'm going to do something here. Now, I'm going to ask you a question. Has there anything been stating that we have to write input a and f of x at two different times? No, I've never said that today or yesterday. But we filled in a, then wrote in f of x, yes? And then we rewrote it with f of x. I do this to help y'all keep track of all of our terms, making sure we're putting them in the right spot and we're not mixing things up. But again, I will say this throughout the semester, if you feel comfortable and feel like you can keep everything in line, there's nothing saying we can't put them both in at the same time. But again, this is a question for yourself. If you feel comfortable doing this, go on and do it. If you think that you might get terms mixed up or get things in the wrong order, do it one step at a time. Does that make sense? Because if you do it like I just did, I'm not counting points off. If you do it step by step, I'm not counting anything off. Because again, this is to help you make sure you solve them all the way out. Because again, we're going to get to the same point. Now this here we have to multiply through. So we multiply with our absolute values. So we'll have 0.25 times the absolute value of x minus 1. We also have to multiply our 0.25 by 2. .25 times 2 is going to be 0.5. And that's it. Now, if you wanted to rewrite these as fractions, if you rewrote the 0.25 as 1/4, solve it the same way, you would have gotten 1/4 times x minus 1 if you wrote it as a fraction. So if you wrote it as a fraction instead of a decimal, same thing. Those are the same answers. Those are the same values. I'm not going to count one right, one wrong. Okay? The only reason I'm specifying this if you convert to fractions, convert everything to fractions. I don't want you giving me 1/4 times the absolute values of x minus 1 plus 0.5. If we're going to be in fractions, let's keep it all in fractions. If we're going to be in decimals, let's keep it all in decimals. And on that note, if it isn't, if it's a kind of 0.6 repeated decimal, we can turn it into a fraction. Let's leave it fractional. Let's try to avoid rounding or approximating as much as possible. All right. Questions on this here? Are you ready for the last thing of 1.3? We're going to skip 2, go to this one here, combining transformations. We're going to combine transformations. Okay, we ready? Let the graph of G be a vertical shrink by a factor of 0.25, followed by a translation 3 units up of the graph of f of x equals x. Write a rule for G. Write a rule for G is just tell me what the function is after we applied these transformations. Now, I'm going to give a name for the middle one because we're going to do this one at a time. Let's call it h of x. It really doesn't matter. And the way we do these transformations, we want to do them in the order in which they were listed. So the first transformation that was listed was a vertical shrink by a factor of 0.25. So h of x in the general form is going to be a times f of x. That's what we're going to do first. The value of a is what?
May I have your attention? May I have your attention, please? It's now time to release the cross-country kids. It's now time to release the cross-country kids. Thank you.
Now at this point here, we can rewrite in f of x. And as we've done up at this point, we would replace f of x with what it's equal to. If you want to skip that middle step between those two, that's fine. And at this point here, we'll multiply those two together and give us 0.25x. And up to this point, all the ones we've done to this point, that's where we were finished, we were done. But here, all that's done is said, yes, the first transformation of vertical shrink by a factor of 0.25, we've applied it. Now we need to apply a translation of 3 units up, yes? I want it to be for g of x. Again, when I'm grading these on the homework or the test, if you end up with the final function being g of x, awesome. If you end up with the last one being m of x, n of x, it's just a name for it. It doesn't matter. So, 3 units up. Our general form was what? F of x plus k, yes? Don't write this quite yet. Because this is the general form of it. Are we applying that vertical translation to f of x? No, because we're applying it to the one we just did the vertical shrink to, yes? That's not f of x, that is. So we're applying it to h of x. Because again, you can write that down. F of x, h of x, n of x, L of x. It's just a way to name the function. In the general form, we use f of x because that's just standard notation. It's saying that we're applying this transformation to f of x. Here, we're applying it to h of x. That's all it's saying. Our value of k in this case is what? Because it is up 3, so it would be plus 3. So we're saying h of x plus 3. Well, h of x is what? 0.25x plus 3, telling us our final function is 0.25x plus 3. Questions? So did that add anything to what we've been doing? Not really. It's the same thing we've been doing, but instead of just doing one of the transformations, we did two. We did one, then applied the next transformation to it. If there was another, we would apply our next transformation to it. It's just we keep doing it one at a time in the order that they're listed. Questions on this here? So our final rule, our g of x is 0.25x plus 3, yes? Now the question is, does the order matter? Let's just say I decided to do, you don't have to write this, you can just watch this. Vertical, we're going to move it up 3 first. So our f of x plus k. Since we're going up 3, it would be plus 3. We replace f of x with its function. Telling me my h of x is equal to x plus 3. So here we can see there has been a slight change between the two of them, yes? Okay. Then we can move on to our g of x. A vertical shrink by a factor of 0.25. Vertical stretch and shrink's general form is a times f of x. Our value of a would be 0.25, and we'd be multiplying it by our function f of x. Yep. So we'd multiply the 0.25 times x, 0.25x, yes? Well, that's the same as the one we just did before, yes? But I also have to multiply that 0.25 by the 3, which gives me plus 0.75. Are these two the same equation? No. Order matters. Order won't always matter, but there are some transformations that are going to affect each other. And specifically, if we look at which ones that they're affecting, because vertical translation is affecting the output values, our y values, because it's moving them up. So the y values are all increased by 2, yes? Vertical stretch and shrink is also affecting the y values. Both of these transformations are affecting the y value of the original function. So if we do both of them, the order in which we do them changes the equation because they're both interacting with each other. If it had been, say, a horizontal stretch or shrink and then a vertical translation, horizontal is affecting the x values. Vertical translation is affecting the y. They're affecting two different things. They're not going to have an interaction with each other because they're affecting two different parts of the function. Vertical stretch and shrink, vertical translation are both on the y. It's going to change how it affects it. And the reason I point this out is because some will say we can just throw those in their corresponding spots, like we had in the general forms on 1.2 of describing the transformation. Throw this in for A, throw this in for H, throw this in for K, we're good. It doesn't matter. No, I just showed it does matter. We can't just throw them in. Now, the way we did it first, this here, I could have just plugged the 0.25 in A spot, plugged in the plus 3 in K. We were good because of the order that it was listed. If they listed in the other order, we would have got a completely different function. I say all of that to say this. If we treat it and list it and do the transformations in the order they're listed, we're going to get the right function. And it will show us how they're interacting in the interactions. We just do it one at a time. It works every time that way. Questions on this here? Don't do that. Do we feel comfortable with these here? Because we can do another one, or I can let you all have the rest of the time. Will not